Okay, the sum now of our work contributions, which I choose in somewhat standard notation to represent by delta W sub I. The sum of those from I equals 1 to n, corresponding, of course, to this partition. We get 1 for each of the n subintervals of this partition. And we shrink the subintervals down in the limit we're going to get the integral from 6,350 kilometers to 6,800 kilometers of what? Of our delta W i's, but in the limit these things approach negative g times big M, little m. Our Ri becomes an R, and our delta R becomes a dr. And again, I'm waving my hands over that limiting process, which you should understand. But that's what you need to have learned in calculus and to be refining in vector calculus. Okay, well, so that's it. That's your integral. And we can write that as negative big G, big M, little m, times the integral from 6,350 kilometers to 6,800 kilometers of just dr over r. Now, antiderivative of reciprocal of r is negative 1 over r squared. Evaluated from 6,350 kilometers to 6,800 kilometers. Okay, now these are in kilometers. Our units of G are probably, we're going to use newtons and meters. So there's going to have to be some conversion, but you just plug in if you know the mass of the Earth and the mass of whatever it is you're trying to raise, and there you have it. Okay, in general, now, what does this mean? Means change in potential energy is equal to what? Let's see, I should have a negative here. What's the change in potential energy as we go from here to here? Well, it's equal and opposite to the work done by the net force. Okay? That means, since you have a negative here and a negative here, in general, your expression is going to be G times big M times little m over R squared, evaluated from R1 to R2. Well, is it going to be that? No, actually it's going to be equal and opposite to that. Okay, and that's a good thing because, and it's not 1 over, yeah it is, never mind. No, it isn't. Writing things down carelessly. Now that's R squared and that's R. Okay, so. Sorry, I know better, but so be it. Okay. This looks like it's going to be negative. But we know that the potential energy increases as we go away from the Earth, as we go higher. So what's the catch? Well, the catch is that R1 is bigger than, R2 is bigger than R1. Here's R2, here's R1. If R2 is bigger than R1, that means that the reciprocal of R2 is less than the reciprocal of R1, which means that when we plug a bigger R2 and a smaller R1 in here, we're going to get a positive change in potential energies. If we go from a closer position to a further position, the potential energy does increase. But this is a little confusing. So, I'm going to just write out the final expression because you can easily plug this in and use the signs carefully and see what you get. You get this times 1 over R1 minus 1 over R2. So that if R1 is smaller than R2, the positive 1 over R1 is bigger than 1 over R2 would be, so that when you subtract these you do end up with a positive potential energy change. And remember, I'm using the definition of potential energy, which everybody is supposed to know and supposed to have known verbatim for the last 2.5 months. Okay? Potential energy change is equal and opposite to the work done by the conservative force. We've calculated the work done by gravity. Okay? The work done to get the thing there is going to be equal and opposite to the work done by gravity. And that's going to be equal to the change in potential energy.